this is the final topic on partial derivatives. The directional derivative. Now, technically speaking, partial derivatives are directional derivatives. Partial with respect to x just gives you the derivative along the x-axis, so the x direction. Pretty sure it's the positive as well. Partial with respect to y is along y, partial with respect to z is along the z, so on and so forth. But you can take a derivative in any direction. And this is your directional derivative. I think I only define that for two variant. Again, it's a limit as h approaches 0, right? And notice that now both variables are changing. And this can be extended to more than two variant. There is something to note, something important to note. Your direction vector u has to be unit.
So you have to normalize it before you take the derivative.
So that's the definition. This is how we would actually calculate it. We now introduce the gradient operation. And again, this is for two variant, but it can be extended out to multiple variant, more than two, right? So this upside down delta is an operator. It's my favorite operator.
Is this what they mean when they say gradient descent?
Doubt it. I think it's a different gradient, not the actual mathematical operator. This is called the del operator. I don't know why they call it the del operator. Because that's an nabla.
Isn't the partial derivative?
That symbol is del. Right, but we'll typically read that as del f to mean the gradient, even though it's actually nabla. And the operator for two variant, I'm going to stick with two variant. Now again, this is an operator. So writing nabla just by itself doesn't make sense, right? And also, that wouldn't make sense. Nabla has to come out first because it's what's operating on F. But you can think of it as scalar multiplication. Nabla F, right? Just notice how it's defined f sub x, comma f sub 1. So it's kind of like that f gets distributed into the partials. The problem is if del f is 0, then the directional derivative is 0 in every direction. right? That means there's no change in any direction. If it's not 0, then your rate of change is maximized in the same direction as the gradient. And its maximum value is the magnitude of the gradient. Right? So your maximum rate of change is the magnitude of the gradient, and it's in the direction of the gradient. Conversely, it's minimized in the direction opposite of the gradient. And its minimum rate of change is the negative of the magnitude of the gradient. And in 3 directions, so in 3 directions, or not 3 directions, that should actually be 4 dimensions, but maybe I'll fix that later. 3, call this 3 variables, and I'll try and remember to fix that. Right, then your del operator in 3 variables would just be that. Partial x, partial y, partial z, right? Now we had this here, right? For a 2 variable, and of course obviously we could do a 3rd variable. If it was a 4-dimensional function or a 3 variable. Well, with the notion of gradients, there's a different way of writing a directional derivative. It's just del f dotted with a direction vector. And again, important to note, that your direction vector has to be unit in length. So that you take its dot product, you're not changing the magnitude of the gradient. All right. Derivative of x squared minus 6y squared at 7, 2 in the direction 45 degrees from the positive x-axis, and also in the direction 45 degrees from the negative x-axis. I'm going to start with.
Wait, does that mean a positive y or negative y? If it's just from the positive x-axis, does that mean up or down?
I'll do that after I calculate the gradient. I'm going to draw it out. First thing I'm going to calculate is the gradient, so I'm going to need it. By definition, it's not that, sorry. That, partial z, partial x, partial z, partial y. So the gradient at the point, what, 14, negative 24? And we can make life easy. by factoring out 2. Now for the directions. We don't need to worry about the third dimension because it's too varied. Right, so we can just look on the xy plane. Now what's changing? Just your 2 independent variables, which one, xy plane. 45 degrees from the positive x-axis.
So how's it
Be that vector. The vector is forming an angle of 45 degrees with respect to the positive x.
So then the negative x-axis would just be down.
If you flip on the other side.
See, no, that's what I'm saying though. Like, how for the x-axis, even if it's from the positive x-axis, how is it? How do we know if it's positive y or negative y sided?
Because it would be on the bottom, it would be negative x, right?
It would be negative 45 degrees.
Yeah.
Negative. Oh,
What is the circumference?
That's the double operator.
The double operator?
It's a nabla.
But isn't the just the triangle also laid out as in changing? Or we
That's a delta upside
That's a
down.
delta, that's a delta.
It's capital delta. So there's our 2 directions. But we can write it just like this, right? That'd be U1. What about U2 though?
It would be too close.
Isn't U2 bad, so bad I wanted to give away one of their options for free to try and get them popular?
Yeah. With that.
Well, so.
I would,
I remember logging into my music one day and having an album from U2 that I never purchased. So apparently they just gave everyone
It was like with the
on iTunes.
yeah, with the
I see
iPhone or
what
whatnot, and then people were trying to find a way to delete it.
Because no one likes them because they're that bad.
that's crazy.
How would you write U2?
Is it,
Seven cosine 45.
First of all, that would be a unit in life.
why is it be negative? Because of the and the sign. Okay.
You wouldn't be incorrect.
Okay. I'm guessing there's
In
a
that.
more correct. Your triple H is one.
And that's technically correct.
So that's kind of correct.
But that's only because it's 45 degrees. If that was 30 degrees, you would not.
Would ask you why.
No, you actually still would be correct if you did that. Yeah, that'd be fine.
asking.
No, but I'm sorry, no, but-
Too far
It's
into
what-
the weeds.
So that is just from reference angles. You could do that. So why would you say negative cosine 45 degrees and sine 45? It's because of reference angles, right? Not using reference angles, it'd be cosine of, was that 135?
45 plus 90, right?
180 minus 45. It's 135, right? That'd be cosine 135 and sine 135. And then using reference angles, yes, it's exactly negative cosine 45 and sine 45.
But I guess if you don't have, so I get what you're saying. If the positive one wasn't 45
No, it still doesn't matter. Right, even if that was, say, it was 30 degrees from the negative x-axis,
and it was, and the first one was
30 degrees is still your reference angle. And it's quadrant 2.
Oh, so you're saying because you know that angle? Okay.
That's the reference angle you use.
I thought for a second that you meant the reference angle on the water flow. I was like, wait, what?
Not even everything that.
Wait, so why would we use like the opposite of it for U2?
Hmm?
Why would we use like 135 for U2?
Because it's the.
Because it has to be measured from the positive x-axis when you
Um,
do cosine sine.
okay,
So it's 40, it'd be 180 minus the 45, gives you 135.
right, okay.
Right, that's that angle that we want.
So would that be, it's all on another? See, if you were a negative person.
No, it's the same thing
I guess unless you're not given that reference angle.
by reference angles. It's the same. Even if you weren't, even if I said 135 degrees from the positive x-axis, you would still write negative cosine 45 and sine 45, they're the same thing. Using reference angles.
It is so funny.
So. The derivative in the first direction is, we said this was 2, and this times what? 7 negative 12.
Yeah.
Dotted with, what is cosine of 45?
Root 2 over 2.
What is sine of 45?
Root 2 over 2.
I mean, you factor out that 1/2. Seven root 2 minus 12 root 2. Negative 5 root 2.
Root 2 or 12?
Should be 2. I don't know why I wrote 12. That's it. Directional derivatives really aren't that different. As long as you remember how to do dot products and partials. For the derivative in the direction of U2. Now you just dot it with U2. Right? Using the reference angle, sine stays the same, cosine is just negative. Again, you can factor out that 1/2, which cancels out the 2. It's now what? Negative 7 minus 12, which is negative 19. So, that's it.
So this is solving for the direction of the.
Directional derivative.
Gotcha.
I remember a derivative is what? Physically. What does a derivative measure?
Radiation.
Rate of change. So you're calculating rate of change of that function in a given direction.
I guess would that be like speed, like speed in a direction?
Yeah, it would be speed in a given direction. No, it wouldn't be speed.
Acceleration.
Wouldn't be speed. Speed is always positive. It would be velocity. What you would have to do is, if you're doing speed, is you have to say which happens to be the speed at which you're slowing down, if it's negative.
Which is negative speed.
All right, one of the common examples is temperature change on a hot plate. At a given point, how does temperature change at a given point?
Yeah, but you
In different directions.
center of energy.
And again, it doesn't necessarily have to be the center, but center could be one of those points. But it's just saying, you're on a hot plate, pick a point, you move in a certain direction, how is temperature changing? It's one of the classic examples of directional derivatives.
You could just touch it and find out. I feel like that's quicker than doing that.
Well, then I'd say, okay, what's the exact rate of change? If you can tell me that, then I'd say pretty good. But of course, I want to leave it. You have how many fingers? 10, so I want it at least 11 times.
I'd go.
At least 21 times. I say at least 22 because there is another appendage for nails. That's actually really sensitive too, so that might work.
That's wild.
It actually is a form of torture too. Hot water, cold water, hot water, cold water. Right, directional derivative. The sum function is y e to the x, point is 0, 3. In the direction, two directions again, first 30 degrees from the positive x, second is 60 degrees from the negative x. Again, first we need gradient. Partial with respect to x is what?
Well, yeah.
Now with respect to y.
Yes.
Evaluate it at the point. 3, 1, right? .30 from the positive, that would be U1. U2 is 60 from the negative.
Is, I'm guessing you're gonna have to get that extreme for the people who want to be. Is it
Partial with respect to y. What's cosine 30?
3 or 2.
Sine 30?
How?
I'll write it that way. What angle would you use if you weren't using reference? be 120 degrees. Go right this way though. Cosine, it would be negative cosine, right? Of 60 and then sine of 60. What is cosine of 60?
1/2.
What is sine of 60?
Root 3 into.
And those are your two direction vectors. Notice that they are guaranteed to be unit. Because cosine of theta, sine of theta is a unit vector regardless of theta. Cosine squared plus sine squared is always 1. So if you write it in the form of cosine theta, sine theta, it's guaranteed to be unit. Right? You don't need to worry about making it units. So, which is why in the definition it gave it to you in that form.
Oh, right, the one you take the magnitude.
Was this F? This was C, right? And I think I used F here. It should have been Z. Remember when you take dot products with scalar multiples? Move all the scalar multiples out in front, multiply them together, and then take the dot product of the vectors. Three times root 3 plus 1.
Wait, is that the distance?
Derivative.
Oh, the derivative.
One minus 3 root 3, right? There's your two derivatives. Oh wait, I'm sorry, it shouldn't be, should it? Is it?
Maybe it's minus 3. 3.
Should be root 3 minus 3. Speaking of operates, like I said, this is a very classical applied problem for directional derivatives. Temperature of a heated circular plate at any of its points is given by 64 over x squared plus y squared plus 2. Here we're going to find the origin to be the center of the plate. At the point 1, 2, we want to find the rate of change of t in the direction pi over 3 from the positive horizontal. really make the shape. I know, didn't I? Oh, because I have to do this. Okay, that's annoying. Oh, that's terrible. At least it's a straight line, but that's definitely not. That's probably more centered. Good enough for that to work. And there's the origin. 1, 2. Now, let's say that point. Just say it's right there. Let's say for argument. The direction we're going at is pi over 3 from the positive horizontal. So first, say what u is. Well, beautiful thing about coordinate systems, right? I can move that back to the origin, can't I? As long as I don't change magnitude and direction. So wouldn't that mean that it's cosine pi over 3 sine pi over 3? What's cosine of pi over 3? What's sine of pi over 3? There's the direction. Now, we need the gradient. Oh, joy. Actually, I don't think that's too terrible. Is that right? I'm defining r squared to the x squared plus y squared. Let me take the derivative. Chain rule, right? Move that up there. Now we evaluate the gradient at our point, which was what, 1, 2? What's 1 squared plus 2 squared?
4, 5,
Plus 2.
7.
Oh, wait a minute.
Should it be squared?
They should be squared, right?
Yeah.
And then 7 squared, 49. And then it's negative 128, because x is 1 for the first component.
Why is it 2 squared?
The whole thing's being squared. Because the function of the denominator is x squared plus y squared plus 2.
Yeah.
Has a power of minus 1. So the derivative being negative, that quantity all raised to the minus 2, and then chain rule.
I got you.
Denominator of the second one is also going to be 49, right? So it's now, numerator is what? Negative 256, right?
And we got that issue floating in there somewhere, right?
The point, yeah.
On this one, I didn't take up the whole page for one.
Well, to be fair, the reason it's taking, I need another slide is because of the problem. This actually what I required one slide if I was doing my. Oh, trust me, you won't be getting problems that take more than a single page.
Oh, I
We'll get there. We'll start with differential equations tomorrow, actually. Should start power series solutions tomorrow.
Oh, I gotta talk to you about that. Okay, gross. Indeed.
Did that be?
Hmm?
Did that one person never show up?
You dropped out, yeah?
Nobody dropped out, by the way.
Oh, well, he thinks he didn't.
My roster still unchanged.
I mean,
It's
yeah,
a differential
he
equation.
probably like submitted the form, but I think it takes on 12 days. Sure.
Right.
It's neither one of the persons.
Derivative at t in the direction of u is the gradient of t at the point dotted with u. Make life easy. You can factor out negative 128 over 49 from del t, right? I think we can also factor out 1/2 from u. That's what, 1/3? That's what we're left with. What's 128 over 49 times a half?
64 over 49.
Now take the dot product. That is your change in temperature.
Celsius or Fahrenheit?
They don't tell us.
It's actually
Kelvin is the SI. temperature,
surprise.
yes.
Surprise.
Does Kelvin even go into negative? Or no?
Kelvin does not.
Does not.
That's why it's the SI.
Who's to say?
Yeah, but like it's a
Once
negative
you
or
get
whatever.
to-
you-
Remember, this is the rate of change.
Oh, okay.
So if it was in Kelvin, it'd be saying it's decreasing
Right.
by that amount. Kelvin per
Isn't it once you
unit of length.
Isn't 0 degrees Kelvin absolute?
Oh dear, you just made a fatal error.
Isn't it absolute?
You just made a fatal error.
0 Kelvin. no
It's
degrees.
0 Kelvin. It's not degrees Kelvin.
Oh yeah. So
You had brownie points for recognizing Kelvin was SI units, and then you said degrees Kelvin.
Yeah, because it's the only one.
So now you just lost those brownie
It's the
points.
only one that doesn't have degrees.
You just lost those. Actually, that's not true.
Fahrenheit doesn't have degrees.
Degree Celsius actually has two ways of saying it. Degree Celsius and just centigrade.
No one says centigrade.
I do.
Nah, the UK people say centigrade.
They call it centigrade, not.
They also put
Degrees.
degrees on toast, so they're not.
You're not on my roster anymore.
Yeah, that was the problem, I just spent the last 40, I spent the last 40 minutes fixing that just now.
Oh boy.
It's because you're visiting sooner, right?
I should be able to get you back on the website, no problem.
Yeah, no, they, I see like the course and everything on Blackboard again, so it should be fine, I guess.
Yeah, should be able to re-enroll you into Blackboard or into WebAssign. Because I just saw you no longer on so I removed you from everything.
Oh, man,
So I'll have to add you back in.
wait, I won't have to pay for CEH.
You shouldn't have to.
Okay.
Because it doesn't actually ever delete you, it just moves you to my drop section.
Uh,
I'll give this to you back. So I should be able to recover.
okay.
I do like that WebAssign is, when you drop it, like saves everything.
Yeah.
So I should be able to get back in, no problem. If not, I'll contact them and I'll fix it.
Okay.
But I'm gonna have to add you back to the site.
Yeah, that's fine.
Imagine doing the homework again.
Bro, if I didn't know when I started that.
Is there really no way that you can change it to have the questions on the board be like 2 attempts instead of just 1? Because sometimes I like.
No, not with the mastering sets, I can't.
So, I had an error. I had an error where it's like, oh, your thing can't be graded, like one question. It was like, it can't be graded. And then it
So I
shows you
think
the,
the attempts is per set, not per question.
and then it shows you the answer, and then I just copy the
That's the
answer.
setup with
and
the
give it to her.
mastery set though. That I can't change.
Because I'm just typed like 3 things because I just fat fingers.
And to be fair, I kind of like the mastery set better than.
Why can't we have that for PE?
problems. Huh?
Why can't we have Cengage?
Yeah, why can't we do that for?
Because it's not a Cengage book.
Oh,
And they don't web us. So the only reason we have it for this class is a few years ago, Cengage and OpenStax went into partnership, where they now have the OpenStax books on WebAssign. This book is not partnered with any publisher.
Cause like, the latest like unit.
Because I would like it. Although to be fair, the book that Cengage uses for different equations is kind of so I wouldn't be using it anyway.
We have 81 questions for PE.
That's what it feels like. The meaty homework is kind of ridiculous. I'm not that professor.
Like halfway through, my hands started cramping, and I was.
No, just wait.
I had to take a break.
I mean, I read everything, so I don't know, but haven't studied out.
Just wait until you get one problem that takes you 9 pages.
Yeah, no, I'm using that last math classes. I'm not getting.
But that's why it's also low risk. The homework's low risk, it's only 5%. Like it's all great.
Yes. I'm dreading the first and series game.
Yeah, that's gonna be tomorrow. Hopefully. I should get it done tomorrow.
Yay, D.
Electrical. Learn how to spell. Electrical potential. And the point is given by natural log squared of x squared plus y squared. Find rate of change of V at 3,4 in the direction toward the point 2,6. Laws of logarithms. easy. That is a lot easier to take the derivative of than the first one. Now, what is partial x of that?
X over x squared plus y squared.
What happened to the one hand?
Vanishes.
Why?
It's just the way the math thoughts decided.
No, there's an explanation for it.
I don't know.
That is the explanation.
A logical explanation, that's not logical.
I don't know how to logically explain
But who created logic though?
True.
Technically speaking, the gods.
Exactly.
What's the rule for differentiating log? dx of natural log of u. U prime over u, right? What's the derivative of x squared plus y squared with respect to x? It's 2 over 2.
Um,
So you
half
just,
over one.
you just
Yeah.
logically explained it. What about the partial with respect to y?
Do you think about why I'm not?
Wow, so bad yesterday. That heat was awful.
Oh my god.
I
was a hundred
wouldn't have been
years.
in. I wouldn't have been in anyway. So
Yeah,
Damn.
I had people over and my friend texted me at like midnight the night before, and they were like, yeah, me and my friend are coming over to use your pool.
Did you guys get a tornado? Or
oh my
Oh,
god.
yeah, it was bad.
It like poured for like 30 minutes, and the trees were like shaking, and then it just stopped.
I
Dude,
had
like,
class.
I was in the gym and I look outside, bro. All the trees in the parking lot.
Yeah, I mean,
What's the gradient at P? So you evaluate that at the point.
30 over 25. Yeah. 4 over 25.
What's our direction?
Even that.
No, I just want direction vector for right now. Doesn't have to worry. You don't have to worry about being unit just yet. Just what is the direction?
Oh, -1. How much?
How'd you get it?
3 minus, or 2 minus 3, and then 6 minus 4.
Why?
Just keep the difference.
But why? Why?
Why?
Starting and ending point.
Yeah.
You're starting at P and you're going towards the direction of Q, right?
Right.
So it's the directed line segment PQ. Is that unit? No. So that you can't use that as your direction vector.
So you gotta take my action, right?
What is its magnitude? There's the direction vector we're going to be using.
And I guess root 5 just comes from like magnitude.
Magnitude.
So 1 and 2.
1 squared plus -2 squared, and then square root of that. And then it's just that dot product as the rate of change. There is something common, right? There's 1/25th common. And then that is what? -1/2. Right, so take the product of the scalars. 25th times 1/5 is 1/25√5. Now dot product. What's the dot product of your vectors? I don't know why I have a vector there.
-3.
-3 what?
-3.
Dot product of the scalar.
Oh, escape.
-3 plus 8.
Yeah.
Right, 1/5√5 or √5/25, whichever one you prefer. Derivative of that three-variable function at the point 1, -2, 1 along the curve in the direction of increasing z. Now first let's find gradient of f. Remember, this is now three variables. So partial x first. Y plus 2z. Partial y. X minus 2y, right? And then partial z. 2x plus 2z. You evaluate that at our point. What do you get? Zero. 5. 2 plus 2, 4. Is that the gradient point? Now, we need a direction. Well, we're told that we're traveling along that specific curve, right? Well, at a point, the direction along the curve is what? Let's just say that's our curve. point, what's the direction of motion? Isn't it that way? What kind of vector is that? It might be unit. R of t would be your position vector.
Oh, velocity, right?
You're not incorrect, but I wouldn't call it velocity. It's tangent vector.
Yeah.
Right, which would be velocity. Because if this isn't a physics problem, we're not talking about position. We're saying, okay, on this curve, what is the direction? It would be a vector tangent to the curve at that point.
And in this case, it's
So we're going to want unit tangent, right? That's what we're going to want. So first we need r prime of t, which is what?
One, negative two. Of,
112 t should be. What t corresponds to our point?
T.
How'd you get the one?
I mean, 1 minus 3 is negative 1. Your t squared is 1. Yeah.
They just find in r of t what t gives you 1, negative 2, 1. Right, so you have three equations. T equals 1, t minus 3 equals negative 2, t squared equals 1. Right, solve for t in one of them, immediately you know it's 1, make sure it satisfies. It does. Notice if it didn't, then this point won't be on the curve and you have a directional derivative. Right, because now you're not even on the curve, so you can't have a derivative. 112. Is that in the direction of increasing z? Yes. The z component is positive, which means z is increasing. There's our direction vector. Now we just make it unit. And so we want the unit tangent. 1 plus 1 plus 4, 6, root 6. There is our direction vector. I really shouldn't do t of t, I should do t of 1. Was big happiness. I'm going to call t of 1. There was nothing to expect out of the gradient, right? So you may see it written this way, and I'm going to hybrid it this way. That's not really what it means. We say that's the vector 112 over root 6. It's really not, right? That's implied to be 1 over root 6 times the vector. Right? You don't have scalar division, you have scalar multiplication. So we sometimes write that. You see it more if you're doing I hat, j hat, k hat. You write the vector in the numerator over something. Because it's easier than putting it all in parentheses. Five plus 8, right? 13. There's your directional derivative again, or you want to rationalize 13 root 6 over 6.
Do we have to rationalize?
I think the convention is if you're dealing with numbers, you generally rationalize it. If it's a function, you leave the square roots in the denominator. I think that's generally accepted notation, but it doesn't matter. I'd accept either 13 over root 6 or 13 root 6 over 6. Running out of time. Yeah, 5 minutes.
I think this one's pretty easy.
So we need gradient of f. That's that. Direction, well, they already gave us it in vector form, which is nice. We just have to make sure it's unit, which it's not. Normalize it.
6. Root 6.
Oh, sorry. 2 over root 6. 2, oh, look at that. Minus 2 is 0. Plus 4. 8 over root 6 should be the derivative, right? Okay. It's sad that I couldn't skip that problem because this one does depend on that problem. Alright, so function of the previous problem, we want to find direction of both maximum and minimum increase, as well as the values of the maximum and minimum rate of change. What is the direction of maximum increase? How is that given?
It's absolute value of the magnitude. Positive.
First off, magnitude is already positive. And that's not a direction, is it? That's a scalar.
This is the slide.
It's the same direction as the gradient
Oh yeah.
at the point.
And then the minimum is just the negative gradient.
And so directional minimum increase, which by the way is also the directional maximum decrease. Is the opposite direction. What's the maximum rate of change? Magnitude of your gradient. Remember, you can factor out of 2. That's what, 4 and 16 is 20, plus 1 is 21. And your minimum rate of change is negative in magnitude. Right. Questions? It's straightforward, right? Directional derivatives is pretty straightforward. And like I said, that actually finishes up, which is fun. Alright, so again, you agree? Okay, so we'll do this for 30 minutes, 10-minute break. Then we start multiple integration.
I got 1.
I got 2.
I just said 2.
I got 3. Alright, so Jack gets 4, 5 answers.
Hang out here.
That one is like around like a couple hundred. It was like
Double integration.
It was like 130 with tax or including.
So remember, the integral is limit of Riemann sums. That means double integrals
that would go.
are limits of what's called a double Riemann sum. You thought calculating a single Riemann sum was annoying. I go for a double.
You just integrate it once and then do it again.
That's iterated integrals. Okay, so
Sorry.
by actual definition, then,
What?
doing a double Riemann sum is a pain.
I know there's gonna be a triple one, right?
Yeah.
Yeah.
Oh my god.
Is there a quadruple or no?
There can't be other than.
Are we saying is this?
We don't do it.
Oh, thank
So it's
God.
up to triple.
We only go up to triple on this course. Right. Visually, this is what's going on. Now we're starting with rectangular region. We will move into a more general region. Right. Now instead of sub-intervals, like we did with single integrals, we have what's known as sub-regions, or in this case, sub-rectangles. Right. And again, for this discussion, I believe we're keeping the delta x and the delta y's all equal for each subrectangle. There's no rule that says that has to be the case.
Oh, so it'd be
Each subrectangle, right? So essentially what you're doing is you're dividing your x into subintervals and your y into subintervals. So there's no rule that says those subintervals have to be equal length, right? So all your x subintervals can have different lengths. They don't have to be equal. All of your y subintervals can have different lengths. They don't have to be equal. Which means the area of each subrectangle could be different. But for general purposes, we're setting it up so that they're all equal, right? So all of your x subintervals are the same, we call delta x. All your y subintervals are the same, we call delta y. In which case, each subrectangle will have the exact same area delta a. But that doesn't have to be the case. And then you pick a sample point from each subrectangle. And again, there's no rule that says that the point has to be chosen the exact same way. As you can see here, the points are chosen differently, right? Here's the center. It's the center of the subrectangle. And there's none that are showing up on the boundary. But you could do a corner on the boundary. If you remember from single Riemann sums, you had 3 methods that were studied. Right endpoint, left endpoint, and midpoint. Right, you can kind of do the same thing. Here you can go like, oh, I'm going to choose like the lower right corner for each rectangle, or I'm going to choose the center of each rectangle, or the upper whatever. Right, that makes it easier, generally speaking, but that's not set in stone. And then you want to calculate the height, right? That's the f of that sample point. And then you sum all of those values up. And that would be the double integral. As you let the number of subrectangles increase to infinity. Yeah, we're not going to do that. Because it's just too much of a pain. I'll save that for a more advanced course. But that is the actual definition. All right, properties, it's still linear, so you still have linearity properties. That's properties 1 and 2 together. Those are known as your linearity properties. You also have you can split your region into 2 non-intersecting regions, except on the boundary. Then your total integral of the region is the sum of the 2. Same thing, you split an interval right at a point. And it's the integral is the sum of the 2 integrals. That's your third property. And then you have your comparison properties, which are very similar to single integrals. This one is new. You take double integral over a rectangular region of a function f of xy. If that function, f of xy, can be written as a product of a function only in x and a function only in y, then you can treat the double integral as a product of 2 single integrals. One with respect to x only, one with respect to y only.
And then you like add the product.
No, it's just a product. Right, you calculate with respect to x, you calculate with respect to y, take the product of 2 integrals. But that is only if it's a function of only x times a function of only y. This is the definition of an iterated integral. And notice what we do. So in this case, dy dx, you integrate first with respect to y. That's going to give you something, and then you integrate it with respect to x. This is a single integral. In 1. That's cap 1. Or 2, depending on what the function looks like in y.
So it's always
But it's a single integral. And it's a single integral.
so if it's like dx dy, you always do the first one first, like the
It's always inner.
inner first.
Right, so this goes together. Then these go together. Right, so it's the integral dy of the integral dx. And then, my favorite, simply because of the name. In fact, I wanted to name my firstborn this. Yeah, my mother wasn't having any of it. Fubini! It's a cool name, Fubini. So Fubini's theorem for a rectangular region says the order doesn't matter. The order you integrate does not matter.
Only for rectangle?
We extend it beyond that. Like for general regions, it says 2. It essentially says it can be written as an iterated integral. Right, so there's multiple Fubini's theorems. Well, so there's one Fubini's theorem, but we break it into different defined regions. Right, for right now, what it's saying is it's only over rectangular regions and the word doesn't matter. We'll extend it later. Well, dA is the area differential. So if you're just integrating over a rectangle, dA, that's the area of the rectangle. Just like if you just integrate a to b, dx, that's actually just the length, a to b. Same thing here. Which means, if I ask you to find the area of a region, which we'll do next time, you cannot use the Calc 1 technique. It's going to break down to be the same thing, but you actually have to set it up as a double integral because this is now Calc 3, not Calc 1.
Is setting up usually the hardest part?
Yes. The setup is the hard. Well, for rectangular, it's not. It's easy in rectangular. But in general, yeah, the hardest part of the double integral is the setup. You want to set it up as an iterated integral. Average value, you should see a similarity. 1 over the area of the rectangle times the double integral over the rectangle of the function. Okay, so these problems are broken into 2 sections. Right. First, it looks at just general iterated integrals. Then it will be the more, find the integral over this rectangle. So here's the procedure.
Yes.
I'm going to calculate that first. Right. Again, I'm not going to do this for every single problem. It's just for, probably just for this one. So first what we're going to do is go the integral x squared x of the y differential. Fundamental theorem of calculus. For part 2. First, find antiderivative. And deal with this, right? And that's just what, x minus x squared? I'll call this I. I now equals again, use fundamental theorem of calculus. Antiderivative. Now, good news is that 0 is just 0, so it's just a half minus a third, which is a sixth. And there's your answer. And there is your integral. And so that is the iterated integral. Antiderivative with respect to x.
Wait, would she be using the 3y for y instead? Oh, never mind.
Let me valuing that interval right now. What is the antiderivative of y with respect to x?
Y dx.
The question is the same as saying the partial of what function with respect to x is just y.
Oh, that's y.
X times 1. Okay. So just like with partials, when you're integrating with respect to a variable, treat all other variables as a constant, right? They're not changing. And was it this class or differential equations where I was asked why I write it that way?
What?
When I evaluate using fundamental theorem calculus, x equals, I forget what course it was that I asked, but this is why. When you start to deal with more than one variable.
Oh, I think it's that.
Good news is, we don't do this in differential equations. You don't have to do multiple integrations for ordinary differential equations. Can't recall if you have to do it for partials or not. So I typically do it term by term. So I go, okay, 9y squared minus y squared is 8y squared divided by 2 is 4y squared. Plus, then it'd be 3y times y, or actually I'll just do 3y minus y is 2y times y. And keep in mind that how I have it written is improper syntax. Should have parentheses around it. Yeah, I'm going to tell you right now, I'm not going to put parentheses around it a lot. Because it's just too much of a pain in the ass to do. It's implied that that dy applies to the whole thing. So that's just this, right? Oops, not good. And that would be 2y cubed. 8 minus 1, 7 times 2. There is the value of the iterated integral. Right. So even this iterated integrals is nothing new, right? It's just taking what you learned in integral calculus and applying it multiple times. If you are rusty with your techniques of integration, maybe brush up on. Because maybe you have to do the method of partial fractions for the inner, and then maybe it's a trig sub for the outer.
I haven't practiced my trig.
Or it's 2 trig subs. You never know. So yeah, you want to brush up on this. Of course, 9 times out of 10, I'm just going to let you evaluate multiple integrals on a calculator. I'll just tell you if you can't use a calculator for a problem. And we're not really testing if you can take an integral at this point. Can you set it up and can you interpret it? But we'll get to that when we deal with some more complicated problems. Well, your project, your group assignment for this is fun. Because I'm having you, I think I did a heavy emphasis on the applications, which I don't cover in class. And I know that I'm having you do the Jacobian, which I do not have time to do in class. So you're going to have to read that section on your own and learn about the Jacobian, and it's essentially change variable in multiple integration.
Is it the same as with like P change of variable?
When I say change variable, I mean like U-sub,
Oh,
but it's not called U-sub, trig sub. Those are all what's put into a category known as a change of variable. So the Jacobian is a general change of variable for multiple integration.
oh, okay.
Really, it's more of a change of coordinate system,
Oh,
but it's the same idea, right? If you convert to a polar, you're doing a change of variable, right? You're changing from x, y to r theta. It's a change of variables. That's what the Jacobian is. It's a more general change of variables, but it's a fun group assignment. So really, it's not going to be a lot of what we're doing in class for that assignment. It's going to be learned on your own, which is the whole point of it. For this one, no bummer, it's not rectangular region, I can't really do that. First, it's with respect to y. Antiderivative of x with respect to y.
why?
Yeah, just yx. I'm actually going to do this even simpler and say, well, since x is constant, it's just going to be x times the length of the interval. X squared minus x squared is 0. X minus negative 2. And that is a trick that I will be using a lot. Top minus bottom. I'll be doing that a lot. Antiderivative of x cubed over 3 plus x squared. By the way, what's that antiderivative known as? That antiderivative has a special name. You happen to know what it's called?
No.
You should.
I forgot.
You haven't even count one. You should.
I was gonna say differential.
Because the actual antiderivative is this, right? It's a family of antiderivative.
Yeah.
What's it called when you set c to 0? The simple antiderivative. Remember that now?
Yeah.
Refer to it as simple. It's when the constant of integration is 0. As you can set it to be anything you want.
Yeah.
And that's what the fundamental theorem of calculus. The fundamental theorem of calculus says any antiderivative. I always use the simple antiderivative. And generally that's what you should be using. Two cubed, 8, negative 1 cubed, negative 1, 8 minus 1 is 7. 2 squared, 4, negative 1 squared is 1, 4 plus 1 is 5. So that's what, 21/3? Oh, wait a minute. So that should be 9/3. It's 2 cubed minus negative 1 cubed. Right, so it's 8 minus negative 1, which is 8 plus 1. And this should not be 5. That should be 4 minus 1, which is 3. And that should be 6. Right, I can't do it. Should have time to do this one. And so it's integrated first with respect to rho. Rho squared over 2 times sine theta, right? You know, good news is 0 squared is 0, so it's just going to be half cosine squared theta sine theta. Change a variable, right? U sub. Just simple U sub for this one, isn't it? Let U be cosine. What's du?
Negative 1.
I don't have negative sign. I have positive sign, so I'm just going to multiply it by negative. Now it's just like U squared, which is U cubed over 3 times a half. 1/6. Cosine cubed theta from 0 to pi. Cosine of cosine of pi. Actually, I'm going to do it in reverse because there's a negative there. So cosine of 0 is 1, cubed is 1. Cosine of pi,
Negative 1.
negative 1, cubed is negative 1. That's 1 minus negative 1. That's 2. D6 is a third. Good?
Yep.
So nothing too complicated, right? Iterating goes fairly straightforward.
Yep.
And just like that, it's the weekend. And don't forget, homework is due Monday. So is the second group assignment that is due on Monday. The third group assignment is in next week's module, but it should already be visible.
Yeah.
You want to get a head start on it. And keep writing, keep filling out your reference sheet. Next time we will start looking at more general regions as well. So have a good weekend.
Thank you. Shit, yo. I don't think anyone understands.